humble rather. Nothing like being not prepared, right? I was prepared. I had everything set up, and then all of a sudden I've lost it. So I've got to go back and get my. So this is the book that we use, and that's the cover of it. So I'm going to go back just a second and get this cover. All right, so I am prepared next time, and here's the cover of it. All right, so this is our book. That's what the book's like. Now, the only problem I have is because this is an ebook, I can't say go to page blah 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 because the page numbers do not show up. So I just have to basically go to a specific area, and then I can kind of we can kind of piece it together. Okay. So there's chapter one, which we basically are going to just skip, which is introduction, and then basically chapter two is kind of a review of EET 1010. So that's what you're going to get. Can everybody see that today? Is that visible for everybody? Okay, so this is what chapter 2 is about. All right? And 2.4. Now, in chapter 3, it actually goes into analysis of these circuits. But in chapter 2, it's just this book is for electrical engineering students. This is an electrical engineering textbook, and it's kind of I don't think it's a circuits I don't think it's like your 1010 course book. It would be more of like a second semester course for electrical engineering students. And then there's a third semester which is called Signals and Systems, which is basically the same as your Laplace. So we're kind of bridging between a second and a third book for electrical engineering students when we're taking this course. This is the same stuff that they get. You're not getting anything any different than they get. So when you're out there and somebody says, well, you're just like a technologist, yeah, but you study the same stuff. In this case especially, you study the same exact stuff. It's not different at all. It's the same course. So that being said, I don't want to scare you. This is the same stuff that you've had before. Okay, so look at this and look at this stuff here. Now, what about from this? By the way, if you want to hear this part of this course being taught by Miss AI, I can just click on this and let them teach it for me. It's this very boring person that is it's an AI generated voice, and I could just turn it on and let them teach for a little while. It's kind of an interesting way of saying, I'm tired of teaching, so I'm just going to click on that. But you would be very bored very quickly. But that's what's at the bottom of this screen. Like, what on earth? Anyway, we're not going to do this whole book. No way can we do this whole book. Okay, well, we're going to do we're not just the highlights. We're going to go deeply into this book and do what really is meaningful in this book to do. And you say this is just about math, and nobody ever said that this has anything practical in it. So I'm going to basically say, is there anything practical in this course? And not much. So I'm going to tell you that there's not a lot, but there is some very practical things that you can say, I understand now why they made us take this course, okay? Now, you know I'm practical. You know that I teach practical courses, but before I was a teacher, I was an engineer, okay, just like you. And I worked in a factory, and I was in a foundry, and I saw a um, big. Uh, it was a pot that they heated brass in. Okay, so this pot that they heated brass in looked like a crucible. All right, looked like this, and they had a connection to it, electrical and water, and they basically put electricity to this crucible, and they had a big control panel over here that had some big old fat capacitors in it, okay? And they had SCRs. No, they had diodes. They had big old fat diodes in it, okay? So they had big, 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 massive diodes. I couldn't figure out what the heck are they doing. They're putting three-phase in here, three-phase AC in here. And they got these, and they got these big, massive ones. I mean, these are big, massive things. And they're heating electricity, they're heating the metal in this using whatever. So somehow they're converting AC to DC because they had a full-wave bridge rectifier here. And then they had these capacitors, big square capacitors. And then they had this. Now, they would tune these capacitors. They had a tuning capacitor, and they would tune this capacitor to be able to heat the metal. What on earth is going on? How can you do this? Is this AC down here, or is this DC? And what frequency is it if it's AC? Okay? Good question. Well, it was DC because they used a full wave bridge rectifier up here. So it's got to be DC. Okay? But what is going on? How can you explain this? This is an inductor because they had these around this crucible. They built a crucible based on they took a coil of wire, or they took metal tubing, copper tubing, as copper, and they flowed water through it to keep the copper from melting. Okay, so the copper tubing was there, but they did it in such a way that it looked like, what is that? That's an inductor. Okay. So with a DC source and a capacitor and an inductor only, what do you have? You have a tunable, no R, just an L and a C with a frequency of 1 over square root of LC. And the only way you can explain that is with second order differential equations. Okay? You will see this later in the course. But the frequency is not the frequency of the AC coming in, it's a higher frequency. The only way you can explain it is with Laplace transforms in a second order differential equation. That's what we're going to be talking about in this course. It's the only way you can explain it, and it works. So if you say, how is this ever going to be practical in my workplace? It can be. It can actually be very practical because you can understand exactly what the circuit is that's working on this to actually make it work. Okay? I couldn't believe it. I thought there's theory over here and there's practical over here. And daggone it, I'm staring right down at a very theoretical problem that is very practical. It worked. You say, how can you possibly explain that? Well, just tune into this course and we'll go through this course. And at the end of this course, you'll be able to look at a problem like this and say, I see exactly how that works. All right? Now, very rarely are you going to see that, but occasionally you will. They wrapped some kind of a coil around ships in World War II to trick torpedoes into not being able to see the ships. And that's another avenue of some of this stuff. And you won't see that nearly as much in this course as you would in an electromagnetics course. But there are practical, very practical applications of, what is the antidote to a certain sensor or a certain area, something that you might build a sensor to do something like how to sink a ship with a torpedo, and all of a sudden they do the other extreme. I've been very interested in this, what on earth they did to these people in Venezuela, because they immobilized them. And I don't know what they did, but somehow they immobilized them with some kind of a weapon. And it was a sound or it was something that they did, and I have no clue what it was. But again, there is an explanation, very, with either sound or whatever, and I'm not going to get into the other side of it. But that's, again, sometimes very practical explanations, that sort of thing. But I don't have a clue there. But I do know this one. I saw it in a factory, or there it is. There is a reason for me to have to study and go through that network analysis course. And it was, okay, I got it. Okay, now, you should be able to do this. Not a question about how to combine resistors. Any questions about that? We got some problems in this chapter about that. And there's a good question right there. If I connect from A to B, what would be the resistance? If I connect from C to B, what would be the resistance? What would be the resistance if I go from A to D? What would be the resistance? That's a good question, and that is a question in the chapter we're going to work on. In other words, you have to look at the paths and you have to decide where the current goes. Now, what is it also about this section right here? We're talking about linear devices, and they talk about linear things. Everything is linear in this whole book. But we're talking about conversion of, this would be a Thevenin equivalent to a Norton equivalent. And if you look at this, say this is equivalent to this. Okay, everybody see that? And so I can replace certain things with other things. Okay, so here's this, replace it, current, here's the voltage source to a current source to a voltage source. We do this all the time. So this is the same as this. 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 So again, this is something that you should, if you've not got in your head, you should review. But this is something that we're gonna take. We're gonna basically say, okay, from now on, we're going to understand that this is a given, and you can flip back and forth anytime. All right, voltage and current division. Voltage divider is your best friend. If you've had me as a teacher, you will know that voltage divider, I use it again and again and again. Current division, I try to never use if at all possible. Current division is not a good friend, because there is an equation for current division if you have more than two resistors, but in general, the best way to do current division is to get it down to two resistors, and then you can just use you can use the simpler rule for that. But it's not nice. So this would be the circuit right here. This is the voltage divider. It's the resistor that you want to see the voltage across divided by the total resistance times the whole thing times the voltage source. Right there is your equation for voltage divider. Okay, now if you have current divider is not a nice animal. Right there is the equation for current divider. Right there it is. Probably don't remember it because you don't use it hardly ever. And I won't use it if I can help it. Okay? Now the goal is to get it down to just 2. And if you can get it down to 2, then it's the smaller of the 2. And don't worry about that right now. We'll talk about it. Here's the equation for just 2. Okay? Current source, 2 resistors. It's the opposite over the sum times the input current. Opposite, if you have just 2, it's the opposite over. So what's the current through the 6.67 ohm resistor? Well, it's 20 over 26.7 times 5. Opposite. But if you have more than 2, if you have 3, 4, 5, 6, then it's that big fat equation, which is pretty hard to maneuver. So the goal always is to get it down to 2, and then you can do it. It's the opposite. Okay, enough. All right, onward and upward. You see what this course is about? Current, voltage, same as we always done. But then we add the S. Yeah, we add Laplace. And there is also multi-sim in this course, but I'll be blunt. I don't use it hardly at all. And when you're taking tests, and there's 3 tests and a final in this course. This is a test-heavy course. But when you're taking a test, you don't have access to multi-sim. And usually I don't even care if you get the right answer. It's just, did you do the right process? Did you do the right steps? If you do the right steps and you can show it to me, if I grade off on it and you say, but I did all the right steps, I did all step, right steps, I just made them, you get most, if not full credit. I'm pretty easy. Why is that done? Because you're being taught to go through and analyze something and come up with a series of steps to get something done. It's doable. It's not easy, but it's doable. Most engineering processes are that. Step, get an answer. And that's why they pay you. So most of the time, these courses are just precursors to saying, are you of a quality that you can actually go out and work as an engineer? All it is. Because very rarely you're going to run into the exact same problems. Sometimes you will. Sometimes some of this stuff will, voltage divider, some of this stuff will come up and you will have to use it, but rarely. But you need to know it because troubleshooting systems requires you to know electrical principles. And what are they trying to do here? Well, if you don't have any idea, you're just, I don't know. But if you have some idea, you can dig in and you can look at it and you can say, okay, I see what they're trying to do here. Either they're trying to do something electronically, or they're trying to do something electrically, or they're trying to do something programming-wise. And you have to mix and do all 3 of those areas and even mechanically, to see whether or not how to fix something or how to get something to run. So it's not just electronics, and it's not just, but it's problem solving is what it boils down to. That's all this is. If you're a good problem solver, they figure you can be a good engineer, and that's pretty much that's pretty much it. Okay, so in this chapter, I want to work through some of these problems, and the first one I want to work through is 2-12. All right, so let's just, you say, are you going to start teaching today? Yeah, I'm sorry. But 212, okay? We don't have any choice. This course is, there's no let up. All right, determine which elements are in series, parallel, or either, and how many different nodes and loops are there in the circuit if, okay, and then it says find if V2 is equal to 3 and V3 is equal to 5, find V1, V4, and V5. Okay, so here is this circuit. Now, how many different nodes are there in this circuit? How many different nodes are there? There's just one, right there it is, okay? So you go from here to there to ground, you go from here to ground, and you go from here to ground. And then that's it, okay? Now, what's the current going through V5? If I have 0 volts over here, and I go through a resistor, and there's 0 volts over here, what's the current through there? 0. That's what we have. Okay, so it's a trick. Now, if you got 3 volts here, and you've got 5 volts here, okay, so this is plus to minus, plus to minus. What would be the voltage here? Okay, the sum of the voltages around any closed loop has to equal sum of the voltage around any closed loop has to equal 0. So we have to say 3 plus 5 plus V1 equals 0. V1 is what? Okay, now if it's a plus is on the bottom side, but we're walking around it the other way. I'm sorry, I got this wrong. It's the plus is on the top, minus is on the bottom. So if we walk around this, if I walk around this loop this way, I meet the minus sign before I meet the plus sign. So I say minus V1 plus 3 plus 5 equals 0. And that's mathematically how it's described. So what is V1? 8. Any questions? Easy peasy. All right. What is V4? So again, I go around this loop. I say, and I don't care about the ground. So I've got plus on the bottom, minus on the top, V4. And then I've got a resistor over here with a voltage V5 equals a 0. And then I've got another resistor here, V3 is what? 5. So I got 5 volts here. So I march around this thing and say, okay, I go around this way and I say minus V3 plus V4 plus 0 equals 0. And V3 is minus 5. So what is V4? V4 is equal to 5 volts. Any questions? Piece of cake, right? What else do they want to know about that? That's about it. It says, determine whether the elements are in series, parallel, or neither. These are in series. They're in parallel with this. I don't know. It doesn't really matter. I'm not going to worry about that. As you can tell, I'm not a, Now, these are problems that I want you to hand in. This is your homework. This is be your, by the way, we work your homework in this course before you have to hand it in. So you're going to be responsible for some of these. And I'm not sure how many we're going to do, but we're just going to start. Do as many as we can today, do as many as we can on Wednesday, and we'll be done with chapter 2. Okay, so that's number 12. Number 13. All right. Number 13 is look at this picture right here, and determine the nodes and at least 5 loops in the circuit. All right. All right, so in this situation, 213, Ted, 213. So this one is, all right, I2 is minus 50 milliamps, and I4 is 15 milliamps. Find I1 and I3. So you can say I1 plus I2 plus I3 equals 0, right? Is that right? And that would be, so in that case, I2 is equal to minus 50 milliamps. So I2 is really going into that node of 50 milliamps. And I4 is 15 milliamps, so I3 is equal to I4 is equal to 15 milliamps. What is I1? Well, it's what's left. I1 is 35 milliamps. Everybody follow that? You got I1 plus I3 is equal to I2, or I2 negative is going out as minus 50 milliamps, so it's going in at 50 milliamps. So 15 of it goes here, 35 of it goes there. And that's it. I'm going to skip 14. I said I was going to do 14, but I'm not. We're going to skip 14. 14 is kind of a mess. Okay, so far we're 212 and 213. I'm going to go down to 224. Okay, now with this one, assign a voltage and current variable to every element. So basically, you've got what? Well, in this one, we've got a bunch. We've got a mess. What we got? These are, by the way, these are kind of strange. These aren't our normal problems, are they? These are not our normal everyday problems, but these are asking us to look at Kirchhoff's voltage law, Kirchhoff's current law, and apply them pretty much just blindly. So it's 2-24. You never build a circuit like this, but a current and voltage variable to every element. So this would be a I don't know what you call this, but anyway, let's just um, use KVL to find the voltage across each resistor. So here in this loop, 15, and here is minus 15, and here's a resistor. Okay, so it's 200 ohms. So what's the voltage across those? What's the voltage across that resistor? Right there, bless you. What's the voltage across that resistor? It's 30. V200 is equal to 30, all right? Why? Because you go around this loop, minus 15 plus V200 minus 15 is equal to 0. And the way you do that is you say minus 15 plus V200 minus 15 equals 0. V equals, that voltage across that resistor is equal to 30 volts. If voltage across that resistor is equal to 30 volts, what is the current through it? It's 30 divided by 200. And what's that, Ted? I got to get my calculator because I don't have the answers to these. Okay, so what is 30 divided by 200? 0.15 amp. Okay. Any questions about that? Over here, what is the voltage? Well, it's the same thing, except this time we're marching around this way, and the current in this case is plus on the right, minus on the left. So the current on the left one is going left to right. The current on the right one is going right to left. So it's the same thing. V200 over here is going to be, okay, this one is the current is going left to right. This one, the current is going right to left. So it's the same thing, 0.15 amp. All right, so we've got 0.15 amp going this way, 0.15 amp going this way. What do you think the voltage across this guy is? 0. Why? Same thing as we had before. It goes, this circuit is this one right here. Plus 15. Plus 15. So here's my 200 up here. This would be this one right here. All right, so it's, I'm marching up, minus 15 plus V200 here, plus 15, because I'm coming in from the plus side, equal to 0. Voltage across the 200 here is equal to 0. So there's no current going through that one. So I've got 0.15 milliamp going this way, 0.15 milliamp going this way, flowing down through here. What's the current going through there? 0.30 milliamp. All right? And then what's going through the current through over there? 0. Everybody see that? Just using Kirchhoff's voltage law, you have to find that. That's your conclusion you have to come up with. Right, and that's number 24. 25 is another one I want you to do. Okay, now this one is find the power provided by the source and the current through the 68 k ohm resistors. So here, this is what? This is that current divider problem that we didn't want you to have to do, but we're going to make you do. Okay, so now we're going to make you either, now here is two choices. In 2-25, either convert everything to voltage, or use current divider. But with only 2 elements, current divider isn't quite so bad. Current divider is a mess with 3, 4, 5, 6 in parallel resistors. current divider with 2 resistors isn't as bad. Everybody follow that? 2 is okay, 3, 4, 5, forget about. So here we have how many paths? 1, 2, which is not so bad. So basically how you choose to do this is up to you. Now, if you choose to do this using voltage only, you've got to convert everything to 1 resistor, find the voltage across it, voltage across here, and then go back and solve the problem. That's an easy way to do it, but you've got to convert everything to voltage. Get it down to 1 resistor, and then use voltage, and then you're done. The other way to do it is to use current divider. Your choice. They both work. That's one of the problems with electrical engineering is, oh my goodness, I have so many choices. Usually you have 2, but you do have more than 1. And in this case, you decide which way you want to go. Okay, now I'm going to work it both ways so you get the idea that I'm not there either way. Okay, so you've done number 24, now you're on number 25. So if I work it with just getting it down to voltage, converting this. Now, the other thing you can do here is look, bless you, is look, you can now say, look at this thing right here. This is another way of doing this. You can say, look at this. What is this? Ah. This can be flipped to this is a Thevenin, or excuse me, this is a Norton. Everybody see that? This little guy right here is a Norton. You can convert Norton to Thevenin and then work it. And I like that approach too. That's a third approach. It's a tricky way of doing it, but it's doable. Now, what is the conversion of this? I'm going to work it all 3 ways. All right, so one way to see this is convert this. You see this is a Norton to a Thevenin. So let's just do that. Let's just say, okay, so what would be the Thevenin equivalent of that? It's what? What's my voltage supply? If I replace this with a voltage supply, what would be the voltage supply? This times this. Okay? This is commonly called R Thevenin. This is called I shorted load. V Thevenin is equal to I shorted load times R Thevenin. That's R Thevenin. This is I shorted load. Okay? So V Thevenin is this times that. Easy peasy. So it's 5 amps times 33K. And that's a big whopping voltage. Okay? That's a big, massive voltage. But that's what we got. All right? And then what do? You bring the 33K up here, make it look like a Thevenin circuit. Then you add the 22K and the 68K, and you've got your final circuit. All right, so the current is now what? I is equal to what? V over R. What is V? It's 5 times 33K over R. It's 33K times plus 22K plus 68K. 33 plus 22 plus 68 is what? $123. All right, so what is I? It's 5 times 33 divided by 123, or 1.341 amps. Everybody get that? Any questions so far? So that's the current through that 68K resistor. Now, what is power? Power is equal to V times I. If you forget power, everybody, you ready for this? Waking up. Is everybody waking up now? Did I wake you up? Here's my V times I right there. That's my power. You can't remember V times I. Remember the stupid professor that's doing this. And then you get it and you say, I'll never forget V times I again. Okay? Sorry for those of you who've had to endure that 3 times, but any questions? V times I? Or I squared R? Or V squared over R? Which one would you rather use here? Which is your choice? I squared R, V squared over R, or V times I? This one. You don't have to do any more. I squared 1.34 squared times R, 68K. What is that? I don't know. Whatever it is. I'll let you finish it. I don't care. You get the picture. That's how you do it. Now, that's one way of doing it. There's 2 other ways of doing it. One way is to convert everything. There's 3 ways of doing this problem. Not just one, not just 2. There's 3 ways of doing this problem. All right, so one would be to say, I'm going to convert this whole thing to 1 resistor. So I'm going to convert 33K and 22K and 68K to 1 resistor. What would that be? Here's my input, here's my output. Okay, so what would it be? It'd be 33K in parallel with 90K. So it would be 33 in parallel with 68 plus 22 is 78, 88, 90. It'd be 90K. So what would be the equivalent resistance to that? Which do you use, the 1 over rule, or do you use the R1, R2 over R1 plus R2? I don't care. They both work. Okay. I like 1 over because it is so, I don't care how you throw me 2, you throw me 3, or whatever, you got it. Okay, so it's 1 divided by, parenthesis, 1 divided by 33 plus 1 divided by 90, parenthesis goes. Okay, that's whatever that is. And I get 24.146K. Okay, so my R equivalent is 24.14K. Anybody not get that? Y'all get that? Kinda? Maybe close? All right, so now we've got our equivalent. So now we've got I, 5 times 24.14K, and that would give me my V right there, voltage across that, okay? What would that be? 5 times 24.14 is equal to 120. Voltage is equal to a lot, 120.7K volts. It's a lot of volts. That's a big lot of volts, okay? Now that we've got that, now I can go back and then find my resistance, or my current through my 68K, which is what? If voltage is that, and this loop is got 90K in it, so 120.7K volts divided by 90K is equal to what? 120.7 divided by 90 is equal to 1.34 amps. Is that what we got before? I haven't worked these yet. I'm working these as we go. So yeah, but you see what I'm saying, okay? All right, any questions about that? What's the other? That's one approach. Now that gets you way away from, I didn't see the the little trick that you did with the Norton to Thevenin and all that kind of stuff. I didn't see that, but if all else comes, just hammer it. You just get it all back to voltage and away you go. Now that way works. So, you know, I got three approaches. I didn't see the one. I can do it that way. I can just kind of like hit it with a big old hammer and that'll work. And it worked. Okay. Now, what's the other approach? The, the approach of the one current, but the other approach would be the current divider, right? Let's see if the current divider works. All right, so here is current divider. I've got 5 amps, so it's 5 times the opposite, which is 33 over this 33 plus 90, okay? And that's the opposite over the sum, 33 plus 90, all right? Let's see if that comes up to 1.34. Anybody take a, do you think this is going to work? Hopefully. This is the weird one because I never remember this one, and I don't use it hardly at all, but it's 5 times 33 divided by 123. 1.34. Ooh, there you go. Okay. Any questions? Any comments? Is the whole course going to be like this? No. We're kind of reviewing today, but this is the kind of stuff that you need to kind of have in your back pocket in order to keep going, okay? We'll stop in 15 minutes. Somebody, if I get going over 15 minutes, if I get going past 9:15, just raise your hand and say you're done, because I can blow right through that. Okay, so let's go to 30. Find the equivalent resistance. That's all this is. This is nothing major. Okay, this is just R equivalent. Okay, so I want you to be able to do R equivalents. Obviously, R equivalent is in 2-30. R equivalent is equal to what? It's 63 in parallel with the combination of 47 plus 100 parallel with 100. Okay? So that's the way I write parallel. I write a little line like that. So it's that, and I leave the K off, and I can put the K back on at the end if I want to. All right? I'll let you do that one. That one's not hard. You should be able to do that in your sleep. All right? 31. This is fun. This is kind of like, yeah, I can see him asking one like this on a test. Okay? This is dumb, but it's not really dumb. And this is a practical problem. Okay, how would you select the switches to achieve an R equivalent of 167 ohms? Okay. Well, you look at this and you say, if the switch is open, what do I get? I get 67 across this. If it's closed, I get 0. If it's open, I get if it's open, I get 100. If it's closed, I get 0. So this is 67 and this is 100. So if I want to get 167, I do what? A. What is switch 1? Is it open or closed? Open. What about switch 2? Closed. Very good. Very good. B. How would you get to get 100? Very good. C. 200. Switch 1 closed, switch 2 open. Any questions about that one? and D. What about this one? 267. Both open. Any questions? Okay. 34. Here's the one in the picture that I told you that was on the thing. All right, find the equivalent resistance between AB, AC, AD, BC, BD, and CD. I'm gonna let you do that one on your own. So that's 34, 37. Find the equivalent circuit for each of these guys. Okay, so what would be the equivalent circuit for A? I'm not gonna do these all, but I'm gonna do a couple of them. 237 A. From A to B, what would be the equivalent circuit? What's the equivalent circuit of a current supply through a resistor? Just a current supply. The resistor is not as of no value. Okay? Everybody follow that? Doesn't matter what the resistor is. If you don't believe that, go back to the section that we just showed you, or go back. If you get the book, go back to that page in the book. If you don't, go back to the place in the video where I showed you those equivalencies, and you'll see that that doesn't matter. Okay? What about this one? Well, that's Norton. Flip it to Thevenin by doing what? This a voltage supply, this times this, and then you move the resistor up to the top. What's this one? Just the resistor goes away. What about this one? They cancel each other out. Anyway. What about this one right here? Voltage supply goes away. What about this one right here? They add together. I'll let you figure them out. That's about all on that one. 30 or 44. Find IX, IY, and IZ. I'll let you do that one. $48. Again, this one may not be quite as easy. If you work on it, 52. And 53. So I've got, altogether, I've got 12, 13, 24, 25, 30, 31, 34, 37, 44, 48, 52, and 53 to work on. Okay. And hand those in a week from today. All right? If you don't have them, a week from today is Monday. Hand them in next period, because that's I don't want to wait a whole week and a half. I would like to do them next period. Hand them in next period, and we'll go on. We're going to go really quickly through uh, resistive and reactive circuits. We're going to review both of them, but we're going to do them very quickly, and then have a test. Test in about 4 weeks. It's going to be quick, and there's going to be 3 tests, and then we get into the adding of the Laplace, and the Laplace gets you into L's, R's, and C's with AC and DC circuits. And that's where it gets, hate to use the word fun, but that's where this course gets pretty sticky. Okay. So, do you buy the book? Do you wait and not buy the book? It's up to you. I usually buy books. I don't know how much this one costs, but I usually buy the books. I used to always buy the books. But again, books, when I was going to school, were 10, 15 bucks. I hate buying a $300 book, but it's up to you. I'll try to make it so you don't have to if you don't want to. Okay? Anybody have any questions? That's the way this course is run. It's not a big deal. I'll post this as a, yes.
How do you want us to submit homework? Like, do we just hand it in?
Yes, just hand it in. Please do not send it electronically because I'll have, okay, I'm going to shut this off.